All right, we're back. We're going to take a look at the third and final of our pressure types that we're studying to build towards introductory applications of what's called Bernoulli's equation. Now, we already introduced the name and the equation and looked at a little bit of units back in our pressure list. The last one that we have to take a look at is dynamic pressure. And this lesson is going to be a little bit different. Dynamic pressure is an interesting one that I think we want to spend some time understanding a little bit conceptually and the implications of it. However, we're not going to really solve any numbers in this particular lesson because I find that solving numerically using the equation for dynamic pressure, which does apply to dynamic pressure, makes the most sense when we actually combine it with our next lesson, which is going to be Bernoulli's equation. So, this lesson is more about giving you an idea of what's going on with this last and I would say one of the strangest applications of pressure that we need to understand and apply this concept called Bernoulli's equation, which is one of the very important introductory steps in fluid mechanics. So, jumping in, we're going to take a look at conceptually dynamic pressure to get an understanding of it. And honestly, this is one of my favorite ones because there's so many cool applications of it. The key idea behind dynamic pressure, actually I'm getting ahead of myself. So if you were in my class, then hopefully I'm still doing this, but I'll go ahead and set it up as a prompt. So in my class, I've got a bunch of these funnels. These are actually lantern oil funnels that you can get at a camping supply store. They are brand new, so they haven't had oil go through them. Make certain you're not using old ones. You want fresh ones. Because here's the prompt that I actually gave my students. There's a ping pong ball, and I'm going to put it in this funnel. And I say the following, okay, we're going to have a competition to see who can actually use this to launch the ball as high as it can go. And if you can hit the ceiling, you get some bonus points in one of the categories. Honestly, I haven't thought of exactly what I would promise on that, because watch what happens. So here's what I'm going to do. We've got the ping pong ball in there. There's nothing fancy about the funnel. It's just a regular funnel. Here's what I'm going to do. And so, if you are one of my students, and I'm still doing this, I pranked you by setting you up, all of you, with the funnels and with a ping pong ball because, for whatever reason, the ping pong ball will not launch. I'm actually going to expand on that to show you a little more thoroughly. This is not a clear funnel, but it was one that I could get cheap and easy to clean, because I can clean them up with a quick sterilizing bath. But here is a funnel that is actually made of glass, a little bit more dangerous and more expensive, but more to the point is clear. So here's what I'm going to do. I'm going to show you the two things because one of these is not very impressive. In fact, I'll start with that one. I can lift up the ping pong ball by breathing in through the funnel. So what I'm going to do is I'm going to push all the air out of my lungs so that you know that I'm only able to breathe in. Not that you necessarily need it for this one, but here we go. And I can hold the ping pong ball up by breathing in. Now, hopefully most of you, hopefully you haven't turned off the video yet, but here's the thing that usually surprises people, and this is a very good funnel for it. Not all of them quite do this, though you could probably do it with one of these. Here's the other thing I can do. I can lift up the ping pong ball not by breathing in, but by breathing out instead. And it's at the heart of why this won't work as a launcher. Okay, so now I'm going to do that thing again, except this time I'm going to take a really big deep breath so you know that I can't actually breathe in because my lungs are already full. I have to breathe out. So here we go. Scene once again. And as long as I breathe out, I'm blowing very hard on this, I can actually lift the ping pong ball up one more time. But as soon as I stop breathing, the ball falls out. The answer to this is actually what we're studying today, which is dynamic pressure. So dynamic pressure is basically pressure change due to fluid motion. You don't necessarily need to rewrite this if you already have the equivalent one in your notes from one of the previous lessons, but I'm emphasizing it here for this to also act as more or less a standalone lesson. All right, pressure change due to fluid in motion. I'm going to go ahead and write the equation out just so we've got it. Pressure P sub D for dynamic pressure is 1/2 rho V squared. In short, this is why I want to take some time with the conceptual and not focus on the math, because as the speed goes up, our dynamic pressure goes up, but that's also something where it gets a little bit tricky. In this case, I want to jump to our actual takeaway on this. The pressure does increase. In short, the pressure in line with the motion, or parallel, I guess, increases, but the lateral pressure to the sides slash perpendicular pressure drops. Okay, and that's the thing. Like I said, this, to me, the equation, I don't usually use it independent of Bernoulli's equation, but in short, when you have fluid flow, the pressure will actually drop to the sides of that motion. And we're going to start going through and actually show how that applies here. The takeaway conceptually is this. Now, this isn't actually supported by the equation, because as we saw with the equation, as the speed gets bigger, V gets bigger, then the term that we're actually solving for, P sub D, the dynamic pressure, actually increases. But that's, so I want you to think about this. We've got air in here, and the air molecules are all bouncing around in all the different directions, and that causes just our ambient pressure, our reference pressure that we talked about in some of our previous lessons. What we can do is we can introduce a flow by actually setting up something like, I don't know, maybe a hairdryer, for instance. And so I can push the air in a given direction. When I do that, the dynamic pressure, the equation we have, is basically saying the pressure increases in the direction of the flow. So if I move all of the flow to the right here, then the pressure pointed to the right would actually increase. So if my face were here and you actually turned on the hairdryer, in fact, let's go ahead and do that. It feels as though the pressure on my face actually increases. But the thing I want to talk about conceptually with dynamic pressure, which is very interesting as far as I'm concerned, is what happens to the sides, the lateral. And here is where these ideas are for what's happening on the sides. If you have a high speed, you end up with a low pressure, and if you have a low speed, you end up with a high pressure. And that's something that we see. So for instance, we could go back over to our funnel. So for the funnel, I'm going to draw that out. We have the following. I've got things here, and then we'll go ahead and take the ping pong ball and represent it here as a circle. So this is my ping pong ball. We've got our funnel, and we've got the ping pong ball. Now you saw just a moment ago, it's still fogged up from my breath, but we had it set up like this. This is a cross section where we're going to look at it from the side. Now, if there's no flow field at all, then we have air at rest here, here, all the way around, and we have equal pressure all the way around, which means we end up with no net force. Okay? So if that were the case, if I just put this in the funnel and let go of it, it falls right out because there's still a force of gravity on it. But in this case, if I actually set this up where I blow into this at a high speed, well, it's going to push in on the top of this, maybe down a little bit, but the air has to go somewhere, so it rapidly gets pushed or redirected to the sides and goes flying past these parts. As we're going to learn in one of our later lessons with continuity equation, if this is a very constricted area, we actually can increase the speed by quite a bit. But in short, we have high moving or fast air here, and we have pretty much air that isn't moving at all down here. And here's where we get that idea of dynamic pressure. So I've got my high moving or fast moving air is going out these ways, and technically out this way too, but underneath the ball is a pocket of air that isn't actually moving. So in this, we have, for the blue ones, we have a high speed, and therefore its lateral pressure, how much it pushes to the sides, is low. However, for our air down here, we have a very low speed. In fact, it's probably pretty much zero, and that means our pressure is at a large value. And so what we end up with is this. The pressure on top, because this is all moving very quickly, we have a higher pressure with the dynamic in line with it, but to the sides, pushing onto this, we have very low pressure on top because of the dynamic pressure. On the bottom, this has a higher pressure, so it pushes up with a lot more pressure, a lot more force on a given side. So on the top half, we have low pressure from the air, the fluid moving very quickly. And on the bottom half, we have high pressure from the fluid not moving at all. So we end up with a net upward force because of the greater pressure on the bottom. Now remember, pressure and force are not the same thing, but we have basically the bottom half of the ping pong ball has a pressure applied to it, which is much greater than the top half, which has a much lower. So when we take the pressure multiplied by the area along the top or bottom of the ping pong ball, that's what turns into our forces. And if the air is moving fast enough that we can get a low enough pressure here and high enough pressure here, then we can actually generate a net upward force, countering out gravity and, depending on the circumstance, actually making it even higher than that. We'll see that towards the end of this lesson. Now, this does have applications, as some people would say, in flight. That being said, I took quite a few classes in aerospace engineering. This only applies Bernoulli equation, which is what we're building towards, can only be applied for low-speed flight, so things like gliders or paper airplanes, or really old-fashioned planes. We learned in our undergrad studies, so I could be wrong on this, and I'm thinking back 20 years now, but you could apply Bernoulli's equation and this concept to explain flight as long as you've got low speed, dealing with about 0.3 Mach or lower, about a third of the speed of sound. Now, that sounds like, okay, speed of sound is still super fast, but most planes are actually going to be much closer to the speed of sound. So modern jetliners, they're going to be well above 0.3 Mach, and therefore you wouldn't actually be able to directly explain how they fly, getting lift, with dynamic pressure. So low speed, gliders, that sort of thing, or paper airplanes, they would be great in actually described with dynamic pressure. Okay, so here's what we saw with the funnel. But let's take that a step further. I've made a claim. Let's test it in a different aspect. I've got the hairdryer. So I can do the following. I've got gravity on the ping pong ball down, and I can have dynamic pressure in line with it. If I point straight up, we can have the push of that air, if you will, and the increase in dynamic pressure in line with the motion to actually hold this up. So here we go. And as long as I keep it going, I can keep the ping pong ball aloft. We have the high dynamic pressure from below pushing up in line with the velocity, in line with the speed. And therefore, we can have a higher pressure than the top, which would have a lower pressure just from the air, the moving air pushing up on it. So that's one aspect of dynamic pressure. And that's the one most people can easily understand. I'm basically pushing up with air. But one thing that's easy to overlook on that is, if that's the case, you see this wiggling back and forth. If it was just pushing straight up, this thing should fall off to the side. It's almost like I have a pencil or something that I'm pushing up on it, and if it goes to one side, it would fall out. I want you to pay extra close attention. It's actually pretty stable. It doesn't fall out. And that's actually your clue that there's more happening there. In fact, watch the next part. Well, it gave up partway through. Let's try that once more. But I think you saw it. So what's happening there? Now you might be tempted to say magic, but it's not. It's dynamic pressure. So let's take a look at this. When I've got the hairdryer down here like this, and it has a flow of air that goes up like this, and we've got our ping pong ball, we've got the following. Like I said, when you're directly in line with it, okay, great, you have a high pressure coming in line with it as it hits there. Although the air would end up going around it, but one of the key things on this is the air does end up going around it, but we've got something that actually counters out the effect of gravity. One of the things that I mentioned is this. Imagine now as this wiggles around, well, if it falls over here, it should just fall out, except here's where we can fill in the additional stuff. We have a column of air that's moving very quickly here, and outside that column of air, we have stationary air that is not actually doing a lot of moving at all. So laterally, in line with this, I should say, we have a high pressure, but the way dynamic pressure works is anything off to the side is actually going to decrease. So we have a low pressure off to the side. However, these have a high pressure pushing back in because they are not moving very quickly. Once again, high speed, low pressure, low speed, high pressure, at least to the sides. So here's why when the ball gets over here, you have, on the sides anyway, low pressure from this fast-moving air, but you have high pressure from the stationary air, and that's why it keeps wiggling back and forth in between. If it weren't for dynamic pressure, it would just fall right out. And in fact, we emphasize this further when I turn this on its side, and we go like this. We can now understand what's happening if we look at our flow field like this. I've got the ping pong ball here. If it's in the direct middle of the stream, then it has no net force from the pressures. It does end up with a net force from gravity pulling down, and so it would tend to fall down. But as it starts to move out of the flow field, you've got low pressure here, because it's to the side of our dynamic pressure, the key thing that I'm trying to get across here. And this, being stationary, has a high pressure, and we end up with, basically we have a pressure up, and then a greater pressure up and to the right. Technically, we have less pressure down and to the left, and so now we end up where it will slide, and basically the rightward part gets balanced out by some of the flow field here. But this is broadly where we can get the force underneath to help hold this thing up. In fact, if I could get this going fast enough, I could actually hold it completely horizontally. And so that's one of the other things. I'm going to go back and show it one more time, but you'll notice if you look at where the hairdryer is, the ping pong ball does not stay directly in front of the hairdryer. It will be slightly off. It'll be slightly down from the direction that the hairdryer is pointed. So let's see that one more time and see the applications of dynamic pressure. So we can see this goes along here, and the ping pong ball is a little below that. Looks like it's going to wiggle its way back out of there. So, why does it not stay completely stationary? Well, partly because I'm wiggly, and partly because of some of the dynamics of this, where if it starts to wiggle some, it'll change the forces involved, and it may wiggle more and more back and forth, kind of like a swing, though I wouldn't say that it actually follows a simple harmonic motion pattern. Okay, that's a lesson for another time. Some other interesting applications. Of course, there's always the old school why plane wings are actually set up with a curve to them called a camber. Oops, not my best wing drawing ever. There we go, a bit better. This has a high camber wing, but you can have the following, whereas air moves quickly across this. The idea, the way that it's usually described is you get the air to move extra fast along the top. It has a longer distance to go. You have shorter distance to go on the bottom. This is all grossly oversimplified. Bernoulli's effect is a way that you can actually describe the pressure differentials that do allow for low speed flight. But I do want to emphasize it's low speed. When we introduce Bernoulli's equation next lesson, and all the lessons that we've seen up to this point, we keep seeing the density grow. And we've been assuming that it is constant. If it is not constant, Bernoulli's equation doesn't apply the way that we would want it to, and all of these pressures end up being a little bit offset. In short, things get more complex when you can squish the fluid. That's beyond our scope for introductory physics, but it is something that does happen in real life. This isn't a bad way of describing it. There are actually other reasons for why the air ends up doing this. If you're interested in looking them up, you can Google things like the kind of Tchaikovsky condition, or go with Kutajikovsky. There was another one that I was supposed to say, but right now I'm distracted, and I don't want to give you the wrong thing. Kawanda effect. Kawanda effect is the other one that you could take a look at. Those are going to give you a much more broader and more specific understanding. In fact, while I have your attention here, we've got that the air effectively, technically it's not moving, but from the frame of reference of the plane, it's coming in horizontally to the left, and it leaves going down and to the left. So, to make it change its motion, to change the motion of the air to direct it downward, the wing has to apply a downward force onto the air to change its motion, Newton's laws of motion. But if the wing applies a downward force onto the air, by Newton's third law, the air must apply an upward force onto the wing. That's a Newton's law approach that is actually very descriptive of how planes end up flying, and one of the reasons why the wing shape can be very useful. Because of fluids, they have a tendency of following along these. In short, another way that you can think about, and I want to emphasize, this really only applies to low-speed flight, but dynamic pressure can actually have an application in explaining low-speed, unpowered flight, or even powered flight if it's not that fast. But other applications that I want to talk about is this. So, I mentioned a little while ago in one of the lessons that we are in Oklahoma. We are known for tornadoes. My understanding is it sounds like a freight train. But one of the things that is commonly talked about when it comes to tornadoes is that the windows break outward. This is something that surprises a lot of people, but this is 100% the case. So I want you to imagine that we've got a house here, and we've got our window here. So we're looking at part of the wall of the house. Okay, let's say that there's a tornado, or high winds for that matter, and they're coming along and they blow, say, into the board along here. So I'm going to draw where we've got maybe tornadic activity or something like that, but air going into the board. I'm going to do a top-down view of this. So we've got our wall here, and I've got my window right here. Window. On the outside, we've got, with the high winds, air moving very quickly. Okay, well that means that it has high pressure in line with it, but low pressure to the sides. And if the wind is blowing past your window, that's the important part. Remember, especially with tornadoes, where this is usually talked about, you've got it where it's curving around, so it's definitely going past the window. It's not really flying into the window because it's curving back around, so we've got it going kind of parallel to the window. On the inside of your house, however, you've got air that's stationary for the most part. So it applies a large pressure onto the window. Now remember, pressure becomes force when you apply that pressure over an area, say like a window. And so when you have low pressure on the outside and high pressure on the inside, then when this thing breaks, if you get the pressure differential high enough, the force becomes enough, and just like our paper towels from one of our previous labs/lessons, it will eventually break. And in doing so, it will actually be pushed outward from the net force being applied onto that area from the higher pressure. So one of the other applications of this, I'm not necessarily recommend that you do this, but this is also why when you've got a car driving down the highway, for instance, and you roll down the windows, anything that gets close to the window appears to be sucked out. Once again, science doesn't suck. It's not actually being pulled out by low pressure. It's being pushed out by high pressure. Now, usually the air on the outside of the car is moving much faster than the air inside, but I guess if you've got the windows completely down, maybe, well, it's probably still going slower on the inside than the outside, but there's less of a pressure differential. One of the last things that I want to mention before we do a final demo on this is do not stand near trains. I can't remember, but I want to think that this was a thing that may have been a TikTok something or other, which is just more reason why TikTok should not be trusted. But we've got a train moving along like this. And as it moves through the air, it actually drags some of the air with it due to air resistance, air friction. But basically, you've got, if there's no train around, then you've got completely stationary air assuming there's no wind or anything like that. And as the train comes through, along with the train, it kind of drags some of the air along with it. It's not moving quite as fast as the train, but trains are also pretty long, is one of the reasons why I bring up a train specifically itself. So if you're standing very near a train, because I've talked with people before that are like, I can stand near the train tracks, it's fine, just don't stand on the tracks or like right next to them, and they'll think that they're just fine, that they could get a selfie or something as the train goes by very, very close. That is a terrible, terrible, terrible idea, and here's why. Because along with the train, as it moves along, you have a pocket of fast-moving air along with it. So on your body, you have low pressure on this side, on the train side. And you have air that is not moving, and therefore high pressure on the not train side. You will end up with a net force, that will then push you into the train. You will not be sucked into it. You will not be pulled into it. You are actively pushed into it by the greater pressure from the stationary air nearby. Okay. Don't get close to trains and be careful around train tracks in general. One of the last things that I'll show you to help emphasize this was another demo that we ended up doing, is a little game where the trick was to try and get let me black out the screen so that we can see this a little bit better. I've got a ping pong ball here in a small container that's about the same size, but it can freely move there. So what I want to do is I want to move the ping pong ball from this container to another container without lifting either of them up and without touching the ping pong ball itself. So here's how I can do it. I can blow directly across the top. This is the key to it. I guess I should have propped this up a little bit. I gotta remember the frame of view of the camera. I apologize. I have to bring this back out. The key is I want to blow across the top so that I have fast-moving air here, low pressure down, and stationary air inside the cup, high pressure up, and that will then push the ball up into the flow field, where the flow field will push it forward, and then it can fall back down. So I can achieve this challenge. Let's see if I can still do this without touching them. Oops. My aim could be better. Let's try that once more. There we go. This is another application of dynamic pressure. Now, in our next lesson, we will stitch all of our studies together and show mathematically how we can start solving Bernoulli's equation to tie all of these together and start to understand plumbing, among other things, a very important thing for our society. All right, until next time.